All right, example 1. Here we're given an equation 2y plus 1 is equal to x squared, and the goal is to find y prime using this relation. So, how do we go about doing it? We derive both sides of the equation. That's our first step. So, let's derive this first term here, this 2y. So, when we do this, this is going to be 2y prime because y is a function in x that we do not know. All right, we don't know what it is. So we just derive it pretending that we did. All right? That's really, really crucial when you're doing these things. You can't make it just go away like if it were an x. If that were 2x, the derivative would be 2. But since it's 2y and y is a function, we have to write y prime, or 2y prime in this case. The plus 1 derives away, meaning it vanishes when you derive it, or is equal to 0. So you have plus 0, if you like. Now you derive the right-hand side. So that gives you just 2x. Standard derivative when you're deriving in terms of x. All right? Simplify this just a hair. Okay? And then your goal is to get y prime by itself, so you divide over this 2. Okay? So you cancel these, you can cancel those, and it looks like your y prime is actually equal to x. All right, so that's the final answer. It turns out, though, at the very beginning of this problem, you could actually solve for y in this case. So if you solve for y, you would get y is equal to, x squared minus 1 over 2. So if you were to try to derive that, you would end up getting exactly the derivative y prime is equal to x. So it shows that this method actually works. But in most cases, you cannot actively find y and then derive it. So implicit differentiation is your friend for when you cannot do that. Okay, so that's example 1.